So, we were discussing critical heat flux, and today we will try to discuss or elaborate the hydrodynamic theory of critical heat flux. Now, critical heat flux will occur on any boiling surface, but to start with, it is convenient to discuss critical heat flux over a flat surface. And again, for the sake of convenience, we will assume that the flat surface is of infinite expansion. That means, the surface is not bound by some walls. So, the edge effects are not coming. Now, critical heat flux on a flat surface we assume that if a Cartesian coordinate system x, y, z is present, where the Earth's gravitational field G that acts in the opposite direction of Z, then the flat surface is extended up to infinity both in the x direction and in the y direction. A representation of the flat surface could be like this. This flat surface is heated, and on the flat surface, over the flat surface, there is pool of liquid. So, during film boiling, we can assume that we can during critical heat flux, we can consider that there is vapor formation. Now, this vapor formation is in an excess quantity, so that this vapor tends to form some sort of a film over the surface, and above this vapor film we have got the liquid. So, the vapor that has to escape, and that will escape in a pattern. So, they will form a pattern of jet, and then they will escape like this from the surface. Now, if we consider the top view of this surface and the vapor release pattern, one will find that the vapor is leaving the surface in the form of jet from each node of this rectangular array which I have drawn. That means, at this node you will have some sort of a vapor jet or vapor column. At this node you will have another vapor column. Similarly, at all the nodes you will have vapor columns. So, these vapor columns are like this. They are not straight, they will have also undulations, as has been shown in this diagram. So, you see there are two instabilities which are operational here. First, a low density fluid, that is the vapor, that is attached to the surface, and above of it there is a high density fluid, that is the liquid. So, it gives rise some sort of an instability which is known as Taylor instability. On the other hand, the vapor jets, they are moving in the upward direction. So, they will have a relatively high velocity compared to the surrounding liquid. So, it will give rise to another kind of instability which is known as Kelvin-Helmholtz instability. So, both these instabilities I have mentioned earlier. So, here we can get some sort of Taylor wave, and in this case we can have some Kelvin-Helmholtz instability. Now, see, this Taylor wave will decide the distance between these columns, and this distance is lambda d. This distance is denoted by lambda d. So, any vapor column will be at a distance lambda d from its neighboring column, and then this is one wavelength of the Kelvin-Helmholtz instability. So, let us denote it by lambda h. And also it has been seen that the jet diameter, if this is the jet diameter, this diameter is given by lambda d by 2. So, more or less this gives an idealistic view of the boiling phenomenon when it is at the critical heat flux. Now, you see there are some salient features of the hydrodynamic model. That means, certain assumptions have been made to develop this model. So, let us see what are these features. Salient features of hydrodynamic model. Of CHF. First thing, the critical heat flux obtained when the surface of the vapor jet becomes Helmholtz unstable. So, CHF needs or requires the vapor jets to be Helmholtz unstable. Second, the distance between the vapor jets is given by the Taylor instability lambda d. Third, the diameter of the vapor jet that is lambda d by 2, lambda d by 2. So, these are very few, very important assumptions that CHF requires the vapor jet to be Helmholtz unstable. When there is a growth of instability on the surface of the vapor jet, that means there will be growth of undulations, and these undulations, when the wavelength will be equal to the critical wavelength of Kelvin-Helmholtz instability, we will have collapse of this pattern, and then we will have the critical heat flux. And then how these vapor jets are formed, or at what pattern they are formed? They are at a distance of lambda d from the neighboring jet, and each of the jet is having a diameter of lambda d by 2. These assumptions have been made. Then another assumption, this was made basically by Lienhard and Dheer, that Kelvin-Helmholtz unstable wavelength KH unstable wavelength is given by lambda t. So, this is another assumption. This was not made originally by Juber, who proposed this hydrodynamic model, but this was later proposed by Lienhard and Thiel. We will discuss regarding this afterwards. Now, then what we have got, this kind of a figure we have got, that if we see from the top the flat surface, then number of jets are coming out. This shows the base area of each of the jets, and the jets are looking like this. Now, here the vapor is moving in the upward direction. So, we can call it UV, vapor velocity UV. As the vapor is moving in the upward direction, so to replenish that, the liquid has to come down in the downward direction. We can call it UL. And we know that Kelvin-Helmholtz instability is dependent on the relative velocity between these two parallel streams. So, UC, that is given by UL bar UV bar. That means, we have to take care of the direction of these velocities also. And this has been proposed, one relationship has been proposed for this relative velocity, which is given by sigma into alpha rho L plus rho V divided by rho L rho V whole to the power half. Here sigma is the surface tension of the liquid, alpha is wave number, and it is given by 2 pi by lambda, where lambda is the wavelength, and then rho L is the density of the liquid, rho V is the density of the vapor. Further, we can tell that rho L is far greater than rho V. So, compared to rho L, rho V can be neglected in the rho L plus rho V term, and if I do that, then one can get the relative velocity is approximately given by 2 pi sigma by rho V lambda to the power half. So, this is the relative velocity. Now, this relative velocity has been calculated from the Kelvin-Helmholtz instability and from the wave theory. There is another way of calculating the relative velocity. What we can do? We can calculate the relative velocity by physically estimating the vapor velocity, which is in the upward direction, and the liquid velocity, which is in the downward direction. Again, one can make an assumption that the vapor velocity is much higher compared to the liquid velocity. So, the UC can be, from physical estimation, UC can be approximated as Q max double prime rho V HLV A surface by A column. So, we are assuming that critical heat flux is occurring, Q max or Q max double prime, that gives the critical heat flux, rho V is the vapor velocity, HLV is the latent heat of vaporization. Now, A surface and A column needs some explanation. So, this diagram, let us go back to this diagram. Let us take this area for our estimation of heat flux. Now, the heat which is supplied to this particular area is responsible for generating the vapor jet. So, how much vapor jet is generated? Here we can see 1/4 vapor jet is generated, here 1/4 vapor jet, and in the other two in each cases 1/4 of vapor jet is generated. So, if I take the distance is lambda d, this distance is also lambda d, and this distance is lambda d by 2. The diameter is lambda d by 2. So, we can see that in a square area of lambda d square, a vapor jet of lambda d by 2 diameter is generated. So, a surface or surface area denotes the area of the square whose side is given by lambda d, and the jet area is given by the circular area of the circle whose diameter is lambda d by 2. So, basically with all sorts of simplification one can get Q max double prime is equal to pi by 16 3 to the power 1/4 rho v HLV sigma rho L minus rho v by rho v square into G whole to the power 1/4. Here of course, one thing is important that we have to assume that lambda h, that means the wavelength of Kelvin-Helmholtz instability, is equal to lambda d, that is the wavelength of Taylor wave, and this lambda d is again given by 2 pi 3 sigma by rho L minus rho v into G whole to the power half. So, substituting all these things, the above equation for Q max that has been obtained. Now, the Q max which has been obtained, here only one very drastic assumption has been made. The drastic assumption is that the Kelvin-Helmholtz instability, the wavelength which is the most dangerous wavelength or critical wavelength, that is equal to the Taylor length of the Taylor wave. Now, this assumption was made by Lienhard and Dheer, of course, without much of a justification, but with this justification, the result which one can get from the calculation of critical heat flux, that gives much better prediction of the experimental data. So, many researchers, they tend to adopt this justification, and then whatever value of critical heat flux we can get, that is the accepted value of critical heat flux. Now, what we have done so far, we have determined the critical heat flux for a flat surface, and that too we have done we have determined the critical heat flux for a flat surface which is extended up to infinity both along the x direction and y direction. Now, in industry or in application, we will have heaters of different geometry, not that we will always deal with flat surface. We can have critical heat flux over circular tube, we can have critical heat flux over other geometry. So, how to determine or how to estimate the critical heat flux in those cases? Whatever we have derived, is it valid for all the other cases? Now, in this direction, some researchers have worked, and ultimately a relationship like this has been predicted. or proposed. So, this relationship says that critical heat flux in other geometry that will be that can be obtained from the critical heat flux which Joubert has predicted or Joubert's theory has predicted, the critical heat flux just now which we have derived, and this is denoted by Q max with a subscript z. This is given by a function of L by LB, where L related to the actual geometry. L is a length scale which is related to the actual geometry. LB is the bubble or capillary length. So, LB is given by, with this expression we are familiar, sigma divided by G multiplied by rho L minus rho V, all within a square root. So, this is the capillary length scale, we are familiar with this. Using this, Lienhard and Dheer, they have found out that Q max double prime divided by Q max Z double prime, that is equal to 1.41 for flat surface. Here I like to say that the theory which we have just now derived, that was proposed by Joubert, but that was marginally modified by Lienhard and Dheer. So, that is why for flat surface what is proposed by Joubert and what is modified by Lienhard and Dheer, there is a difference, and this difference is given by this number 1.41. Another important case is that the critical heat flux over a circular cylinder, horizontal circular cylinder. So, in that case again Lienhard and Dheer have obtained this relationship. This is equal to 0.1 for large horizontal cylinder. So, this is some sort of workable method for determining critical heat flux, and in different books or handbooks one can get this Q max double prime divided by Q max Z double prime for different surfaces, which can be used as and when required for design or analysis purpose. Now, the hydrodynamic model of critical heat flux, it is not free from criticism or limitation. If we list down the criticisms, then it is like this. Firstly, critical heat flux is a phenomena which is culminating from nucleate boiling, but what we are doing for predicting critical heat flux, we are proposing altogether a new phenomenology. The phenomenology which we have used for describing nucleate boiling, that phenomenology is not being used here. We are bringing some sort of new physics or new explanation. So, CHF theory not having relationship with those for nucleate boiling. But it is one of the phenomena when I mean it is a phenomenon related to the nucleate boiling, or it is the terminal phenomena of the nucleate boiling. So, it should not be totally unrelated to nucleate boiling, but that is what we have done in this particular case. We have proposed a entirely new physics for the explanation of critical heat flux. So, many people has got reservation for this. Secondly, the critical heat flux phenomena, the way we have described, we have not taken care of. It does not take care weightability of the surface. Then it does not take care the surface roughness. These two parameters are of paramount interest, paramount importance in case of nucleate boiling, but the critical heat flux theory do not include this one. So, obviously, these are the weakness or limitation of the hydrodynamic theory of critical heat flux. There are other theories of critical heat flux. Already I have mentioned there is micro layer, during boiling there is a micro layer formation, which I have explained earlier. So, from the micro layer point of view, again one can have some explanation for critical heat flux. So, due to lack of time we are not going into this, but basically from the force balance and basically from the from the methodology which Juber has mentioned, there have been efforts to include the effects of weightability, contact angle, etc. One relationship probably can be told, that is due to Kundlikar. So, Kundlikar, he has taken care of the effect of surface weightability. So, in terms of contact angle, the surface weightability he could take care of. So, he has proposed a relationship like this: Q max is equal to rho v H L v plus pi by 4 1 plus cos of theta cos of capital omega to the power half multiplied by sigma into rho L minus rho v by rho v square into g whole to the power 1/4. So, this is a lengthy correlation or lengthy expression. It is not a correlation, it is a lengthy expression, but one can make it shorter if we take the ratio of q max double prime to q max z double prime. Here theta is the contact angle, and there is another parameter which has been incorporated, that is this capital omega. So, capital omega takes care of the inclination of the surface for with the horizontal. That means, this particular expression is not only valid for horizontal surface, it is also valid for critical heat flux from a surface which is inclined at an angle capital omega with the horizontal, and let us say this kind of vapor release pattern is there. So, this relationship is really an extension of the earlier relationships of critical heat flux. firstly, it takes care of the inclination of the surface on which boiling takes place, and secondly, it takes care of the contact angle of the surface, which is very important in case of boiling. Now, if we make some sort of a comparison with the classical theory of critical heat flux and the relationship which has been given by Convective. So, this is Q max Z. The classical theory is independent of the contact angle, which is theta. Let us say we are thinking of a variation of contact angle from 0 to 120 degree. That means highly weighting to highly non-weighting type of contact angle. So, the classical theory will not predict any sort of variation of critical heat flux. And if we now calculate critical heat flux from Convective relationship, we will see that as the contact angle increases, we will have a fall in the critical heat flux, and that fall could be quite large when the surface is becoming non-weighting. This particular graph is for a typical angle omega. Let us say it is for omega is equal to 0. So, so you see that for critical heat flux, we have got some hydrodynamic theory which has got other limitations, but as the critical heat flux is quite a complex phenomena. So, with this theory, at least certain aspects of it we can explain, and it has got reasonably good success in predicting the experimental data. But there are again some variations, there are again some sort of discrepancy, like it has been seen, it has been observed that if we go for the theory which fits well the boiling data from smooth surface, if we go for rough surface, then Q max increases 25 to 30%. So, this is also observed. So, one have to be careful while applying or adopting the result which has been given by the hydrodynamic theory. Now, let us go to another mode of boiling. So, we have discussed the nucleate boiling in detail, then we have discussed critical heat flux in detail, which is very important from the safety point of view, from industrial application point of view. Then we are coming to film boiling. Now, film boiling is not a very desirable mode of boiling heat transfer in most of the applications. So, people want to avoid film boiling in most of the application because it not only it gives a very low rate of heat transfer, but it can also lead to the failure of the heating surface. But even then, sometimes it is not avoidable. So, one needs to know how to analyze film boiling. So, film boiling, the heated surface is covered with a film of vapor. So, this is your vapor film, and at the top of it we have got the liquid. And obviously, the vapor film, as it is having lower conductivity and it is some sort of a vapor. So, it will act as some sort of insulating layer, and the rate of heat transfer will be much lower compared to the nucleate boiling. Now, what will be the heat transfer coefficient? That depends on many factors. One of the factors, that is the orientation of the surface. Let us very quickly see two very common cases. One is a horizontal surface and another is a vertical surface. So, let us consider the film boiling over a horizontal surface. If the surface is wide enough, that means theoretically it is extended up to infinity both along the x and y direction. So, one can expect to see this kind of a pattern. There will be thin film of vapor over the surface, and the film will be interrupted at regular interval by some dome like structure through which vapor has to escape. So, the film thickness can be denoted by delta, the nose radius of this dome that can be denoted by RB, and the length, this can be denoted by L. With some simplifying assumption and by the conservation equations like mass conservation, momentum conservation, one can determine all the geometrical parameters, that is L, RB and delta. In fact, long back Berenson, so in the early 60s, he has given a theory, and from which one can calculate all these things. Now, so what he has proposed, that it is a standing Taylor wave and there is a laminar flow of vapor. With this assumption, one can calculate what is delta. So, delta, that is the vapor film thickness, that can be calculated as 1.09 C, which is a constant, mu v, that is the viscosity of the vapor, K v is the conductivity of the vapor, delta T is the temperature difference, divided by rho v, G, delta rho, the density difference between the liquid and the vapor, HLV, HLV dash, this is some sort of modified latent heat of vaporization, and then our known parameter sigma divided by G delta rho, all within a bracket and to the power 0.25. So, delta can be obtained by some sort of mass and momentum balance by this particular equation, and C is some sort of numerical constant. Now, HLV dash, that is some sort of modified latent heat of vaporization, because there is the wall is at a temperature T wall and the liquid could be at T saturated. So, there could be certain amount of degree of superheat for the vapor. The vapor need not be at the saturation temperature. So, there is a way of calculating it. So, this will be HLV 1 plus half CPG, this is the specific heat of the vapor, TW minus T sat divided by HLV. With this, one can also calculate the convective heat transfer. The convective heat transfer, that can be calculated as divided by mu v TW minus T saturated and sigma divided by G into delta rho whole to the power 0.25. So, this gives approximately the convective heat transfer during film boiling over a horizontal surface. Now, this convective heat transfer depends on a number of properties, you can see number of fluid properties, and these properties are mostly the property of the vapor, and of course, some property of the liquid is important. The density of the liquid is important. So, density of the liquid one can determine at the saturation temperature, but vapor you see at one end it is at saturation temperature, at other end it is at the wall temperature, which is quite high. So, the properties of the vapor should be calculated at some sort of average temperature. So, this shows the case of film boiling over a horizontal surface. Most commonly we encounter film boiling over a vertical surface, and there have been a different way of estimating what is the heat transfer coefficient. So, this shows a vertical surface which is at a constant temperature. This vertical surface is adjacent to a liquid which is at saturation temperature. This is liquid, and as the wall temperature is quite high from the saturation temperature, so film boiling is taking place. Now, the liquid could be moving with some velocity or liquid could be stationary. If the liquid is stationary, then one will have some sort of a velocity profile like this. The velocity profile is such that the velocity is 0 at the wall and the velocity is also 0 at the interface. One can also sketch the temperature profile. Temperature profile of course has to reduce from the wall temperature Tw to the saturation temperature, which is Ts. So, in general this is showing the nature of the temperature profile, but many cases one assumes some sort of a linear temperature profile. The underlying assumption is the vapor film is so thin that only conduction is effective in the vapor film, convection is not taking place. So, we can do the analysis based on certain assumptions. So, assumptions if we note down, one is constant temperature surface, then laminar flow of vapor, third stagnant liquid, then fourth negligible viscous dissipation, then we can also assume constant properties. So, if we make all these assumptions and based on these assumptions we can write the momentum balance for the vapor phase. So, if we write the momentum balance for the vapor phase, vapor momentum balance, we will have mu v d2v dy2 minus g rho L minus rho v is equal to 0. So, it will be convenient now if I show the coordinate. Basically, we can take z in the upward direction and y in a direction normal to the plate, and this is the direction in which gravity works. So, with this we will get this momentum equation. So, the momentum equation can be solved with appropriate boundary condition. So, the thickness of the vapor film is delta, and you can see delta is changing with the height, that is z. So, if we have denoted the velocity as u, so boundary conditions we can get u is equal to 0 at y is equal to 0, u is equal to 0 at y is equal to delta. So, these two are the boundary conditions for velocity. So, very easily one can find out u as a function of y, that is a quadratic equation in y you will get for the velocity distribution along the direction of y. Then for vapor flow rate per unit width of the vapor film, you will get tau v is equal to rho v So, this will give you the vapor flow rate per unit width of the vapor film. Considering only conduction through the vapor film, considering conduction to be the mode of heat transfer, one can get HLV d tau LV d tau V dz is equal to kV T wall minus T saturated by delta. Now, using this equation and the equations which we have derived earlier, using above equations, one gets a differential equation in delta. So, then delta can be solved, and if we solve delta, we get like this: delta is equal to C So, this is the equation we can get. So, where C is a constant and C depends on the dynamic condition of the interface. So, you see delta, then we are getting delta as a function of Z, and other things of course are the fluid properties. So, as we have already shown the schematic of film boiling over a vertical surface. So, delta, that is changing with Z, and that is what we have got from this relationship. So, it is not a linear relationship, it is a non-linear relationship. based on simplified assumptions. Once we have got delta, we can get H film heat transfer coefficient of the film boiling, that is kV by delta. So, this is a very simple but profound result, and using some simplified assumption we have got the relationship for heat transfer coefficient. And based on this, there are number of modifications done based on this. One modification is that we can include convection. Okay. The solution will be little bit difficult, complex, but we can include convection. Then another modification is that we know that this is the saturation temperature and this is the wall temperature. So, there could be some sort of superheating of the vapor, and this superheat can be taken care of by modifying the latent heat of vaporization. This is another modification. But what is more important, that the wall temperature is quite high, and at that high wall temperature, at that large wall temperature, along with convection we have got also radiation. So, to make a proper estimate of heat transfer from the surface, we should do H wall heat transfer coefficient should be H film plus H radiation. Again, there are ways how one can do it. Lastly, I want to say another thing, that the analysis which I have done is having lot of limitation. We are assuming that the vapor film is laminar, but after certain distance the vapor film becomes turbulent. So, again for this portion then the turbulent analysis is important. Then in many cases one can see that the vapor film we have assumed this is a smooth interface, but it is not like this. As I have told, there is Kelvin-Helmholtz instability if there is relative motion between parallel layer of fluids. So, due to that there will be undulations. These undulations will of course increase the heat transfer to some extent, but at the same time they make the analysis more complex. So, there are issues in film boiling which cannot be captured with the simplistic analysis which we have shown. There are issues like other geometries, other complex geometries. There are issues like the effect of fluid motion. So, this is just a beginning. And the last thing which I like to tell, that in between nucleate boiling and film boiling there is another regime of boiling, that is called transition boiling. Now, our success rate for estimating transition boiling, for relating transition boiling, for explaining transition boiling is the minimum. Nucleate boiling we are partially successful, film boiling we are partially successful, but transition boiling really we are not that successful in predicting. Fortunately, transition boiling does not occur over a long period of operation or over a long range of operation. That is why we did not bother about this transition boiling so much. Many cases what is done, that we know the relationship for nucleate boiling, we know the relationship of film boiling, and transition boiling people think that it is a mixture of nucleate boiling and film boiling. So, they can do some sort of weighted average of nucleate boiling and film boiling to predict the transition boiling. That is most of the cases that is what most of the cases is done, but obviously we do not know much regarding the physics of the transition boiling. So, with this I like to conclude this series of lecture. This has given you some background of phase change heat transfer, but our focus was mainly to boiling heat transfer, and we have concentrated only on boiling heat transfer. Condensation heat transfer is completely different from boiling heat transfer, and that could be covered in some other lecture series. Thank you.